title that I have selected is related to development of the radiation resistant ceramic for nuclear energy applications. So as Professor introduced during, so in that one he explained or like that one. So before joining JNU, I was working as a scientist at University Accelerator Center, and that is a user facility, and the particle accelerator is there. So most of the work that I am presenting here, that I have done carried out at IUAC. So I am coming from the JNU. So for Indians, it doesn't require any introduction about the JNU. So it is ranked second among the all Indian universities as per NIRF ranking 2020, and it is number one university among the central university in India. And at JNU, I am taking care of this advanced material research laboratory at School of Physical Sciences. So in that one, mainly I am working on ceramic materials, and these ceramic material can be used for nuclear energy application or like that one. So whenever we will talk about nuclear energy, first thing that come in our mind is like what type of material that is being used as a fuel, and as well as component of the nuclear reactors. And do we need some advanced materials, or can we improve it so that they can be used for some advanced nuclear reactor? So mainly that in nuclear reactor, that material is being as a fuel is uranium dioxide, plutonium dioxide, or thorium dioxide, or like that one. Okay, and this one is schematic diagram of the fuel pellet. So normally fuel pellet in nuclear reactor is like it is 10 mm in diameter, or and grain size of this fuel pellet in the beginning it is in micron size like that. It is like 10 micrometer like that one. And you know that when this fuel pellet is exposed to the radiation in nuclear reactor, and as a result of that, there is a fragmentation in the grain. So in the beginning, grain size will be in micron, and when it is exposed to the nuclear reactor for 3 years like that, so after that, this micron grain is converted into nano grain. So okay, so that way, nanotechnology is very important for this nuclear reactor business or like that one. Okay, so the main important thing is that when material is in micron size, so it have different mechanical properties. Okay, and when it will become in nano grain size, or sometimes it become as a powder, so in that case its mechanical properties are degraded. Okay, so we need some materials, or we can say some radiation resistance material we need it, so that material can sustain in that environment, and there is not any fragmentation of the grain due to ion irradiations. So that's why it is a very challenging area. We need to design some materials so there is a not any grain fragmentation due to ion irradiation. So that is the one area that in collaboration with BRC we are working in this area. Another area that we are working is on the development of again some accident tolerance fuel. So like again it is fuel have a very good mechanicals and thermal properties, so that in case if there is any nuclear reactor, this fuel pellet will be not disintegrated or like that one. And recently we have also started another area that is high entropy alloy, because you know that in conventional alloy like steel, we are adding a small amount of the impurity of the carbon or like that one. So in 2005, this new alloy has been proposed theoretically. So in that one, all the element of the alloy will be in equal proportions, and these alloy will be so very good mechanical properties, and that's why in advanced reactor they are expected to be operated at a very high temperature, and as well as high dose of the radiation. So it is expected like that these alloy will be work in these extreme conditions. So this new area that we have started in that one, and we are also working on like 2D material for gas sensor. But and the most important thing that in today's talk that I'm going to discuss about this spent nuclear fuel, because you know that main problem with the nuclear energy is that how we can dispose these fuel that is coming from the nuclear reactor at safe, repository like that one. So today's my talk is mainly related to development of the materials, and that material we can use for disposal of this spent nuclear fuel. So this one is plan of my outline of my talk. First, I will discuss importance of the ceramic for nuclear industries, and then because students are there, so I also added how we can synthesize these ceramics. So there are two techniques that we use. One is standard solid state reaction technique, and another one is gel combustion technique. So briefly, I will explain about that one. And then we have designed this advanced ceramic by changing the composition and microstructures. And finally, I will conclude my talk. Okay, so now what is this fuel palette or spent nuclear fuel? So this one is cross-section view of the fuel palette, and that fuel palette has been irradiated in nuclear reactor, and that is known as a spent nuclear fuel. So in that one, 96% is uranium dioxide only, and 3% it contains the fission fragment, and 1% is transuranium element or like that one. So this is the cross-section view. So if we will move from the center to the periphery, so at the center you can see it is mainly containing uranium dioxide, lanthanide, and actinide oxide like that one. Okay, and at the periphery, these are the we can say like micron grain lanthanide and actinide uranium dioxide. And at the grain boundary, you know that during nuclear reaction, some gas is also evolving like xenon, krypton, and iodine. And these gases, they accumulated at the grain boundaries, and they form a bubbles-like thing like that one. So as a result of that, it also lead to be degradation in the mechanical property of the fuel palette. And at the periphery of this fuel palette, so this is known as a high burn-up area, and in that area, it is unleashed of the plutonium, and some metal is also precipitated in this thing. Okay, but main thing that I want to highlight here is that in this fuel palette, that is lanthanide and actinide that is containing in spent nuclear fuel, their lifetime is very large, like in millions or billions of years. So that's why we need some strategy. That way we can design some materials. In that material we can dispose or this fuel, and that can be put it in some deep geological site. Or another one is that by intensely we can degrade these materials. So that study is known as a advanced nuclear reactor, that is accelerator driven subcritical system or like that one. And another thing that is again important in this case is that gases that is releasing in atmosphere, because till now, to the best of my knowledge, there is this spent nuclear fuel has been not disposed by any countries. Mostly they are at nuclear reactor site. So that's why continuously these radioactive gas like iodine, so that is continuously emitted in our atmosphere. So that's why it is very important area. And if we will go in our country, so except the many people are not working in this area, so I will advise the student a lot of scope is in this area, and they can start working on this area. So now question is coming, what should be the property of that material that we can use for disposal of this thing? So earlier people have started using glass as a material for disposal of this thing, but glass have some property like that it can degrade in acidic environment. So that's why it is not suitable. So then there is a requirement of other properties required like that. First thing is that any material that can be used for disposal of the fuel is that it can able to incorporate various type of valencies of the actinide, because you know that fuel is spent nuclear fuel is very complex in the nature. Then another thing is that it can able to contain high waste loading. Okay, because otherwise volume of the fuel will be very high, and then it should be chemically, physically, thermodynamically stable, and it should have better leaching resistance in aqua environment. And most important property of this thing is that it should be radiation resistant, because radiation is continuously emitted by these radioactive elements. So then there are people have started work on this crystalline ceramic waste form, And then there are many materials that has been proposed for this type of thing. Among them, these pyroclore structure material that you can say, they are showing most of the property that is required for this thing, like very good aqua durability, high chemical flexibility, high waste loading, and volume swelling is medium. And most important thing is that they also have natural analogous, means in nature we have some rocks, and from many years they are containing these radioactive elements. So if we can synthesize ceramic like these rock that they have, and that can be used. But another important thing in this case is the radiation tolerance will depend upon what type of cation that we are selecting here. So that's why we have tuned this one and then we design it. So what is this pyroclore structure? So basically pyroclore structure, it is A2B2O7 type structure. So here A is can be a lanthanide and actinide, and B will be a transition metal. And then these pyrochlore have a two type of structure. If the ionic radii of the A and B, they are same order of magnitude. So in that case, A and B, they can easily swipe their position, and as a result of that, that structure will be formed. That structure is known as a defect fluoride structure. Okay, but if there is a large difference between the A and B cation, so they cannot change their position, and as a result of that, that structure is formed that is known as a superstructure or pyroclore structure. So in that one, A and B, they will take a particular crystallographic site like 16D or 16C. And most important thing in this case is because this is a derivative of the fluoride structure, so ideally it should be A2O8. So there is a oxygen deficiency there because 7 oxygen is there. So one oxygen site will be vacant, and depending upon the size of the A and B, this X parameter is also varying. So the stability of this pyroclore structure will critically depend upon the ionic radii of Ra and Rb, and it should be between 1.46 to 1.78. And this X parameter, that is 48F, that should be between 0.3125 to 0.375. And this pyroclore structure can converted into the defect fluoride structure by if we can irradiate it or effect of the temperature, pressure, and composition. So that's why these material, they have a very rich chemistry and physics, and lot of scope is there for this one. So now question is coming, if I will take A and B as a lanthanide or transition material. So in that case, there are more than 500 different type of pyrochlore we can synthesize it. So which one we should select it? So that one, there is some theoretical calculation has been done, and in that one, what they have done is that they have calculated how much energy is required if I will change from A to B side or B to A side. So that red zone that you can see. So in this one is this anti-side defect formation energy is very high. Okay, so if I will select a material like this thing, I can say gadolinium titanium oxide, this one. So in this case, this anti-side defect formation energy is very high. So if I will irradiate this material with a energetic ion, so this energetic ion will not able to swipe their position. Okay, so that's why this material, whatever energy that we will use it, so this material will be easily amorphized, or like disorder will be created. If I will take a cation like gadolinium and zirconium, so in this case, size of these two is similar, or maybe we can say like a difference between the size is small. So that's why they can easily able to change their position, and as a result of that, this material will be not degraded or amorphized if you will irradiate for a long time. Okay, so that was the theoretical idea when we started this work. In addition to that, there are another report from the this in physical review paper. So in that one, they have explained radiation stability will also depend upon structure of the materials, melting and crystallization temperature of the material, and ionicity, bond energy, hardness, and microstructure. So these are another way parameter. They also decide the radiation stability of the material. So on the basis of that, we have decided to select these two materials, gadolinium titanium oxide, gadolinium zirconium oxide, and that we have synthesized it, and then experimentally we check it. So the technique that we have used for these material synthesis is a very simple solid-state reaction technique. So we have taken these reactant, we have taken it, and that we have done calcination at 800 degrees centigrade for 2 hours, so that if there is any water or moisture is there, so that can be removed. After that, we have done weighing of this one, and then in stoichiometry amount. Then we have done grinding and put it in furnace for 1200 degrees centigrade for 24 hours. After that, we went to X-ray diffraction, and we checked the phase, and phase was the north form. So again, we have done the grinding, and second heating that we have put it in 1350 degrees centigrade for 36 hours. So after that, from X-ray diffraction, we go single phase. And since you know that for this waste form application, we need highly dense material. So again, we regrind the material, make the pellet, and put it in the furnace for 1450 degrees centigrade for 50 hours, so that we can able to increase the density. And in all the pellet, density was more than 90% of the theoretical value. So this one is X-ray diffraction data of this one. So the peak that mark as a star that you can see, these are the characteristic peak of the pyrochlore structures. Okay, so you can see this one is pure GTO, and as I am adding zirconium in this thing, you can see peak intensity is decreasing. And the reason is very simple that I already explained. Is this one is a boundary line pyrochlore, and it is very difficult to make a pure pyrochlore phase in GZO. So this peak is available because if you can do in low scale, then this peak is clearly visible. And then this one is this how the peak is shifting as we are adding zirconium, and we also calculated the lattice constant, and there you can see it is linearly increasing as we are putting more and more zirconium. The reason is very simple, because the ionic radii of the zirconium is higher than the titanium. In addition to that, we have also done refinement of this data using virtual refinement, and from there we calculated this X parameter, 48F oxygen parameter, and that we have seen it is increasing linearly, and there is a sudden jump is there if I will change zirconium from 1.2 to 1.6. So what would be the reason for that, and is that is important for us or like that one, that you will see. After that, we also done the scanning electron microscopy studies on these samples. So this one is pure GTO, and this one is GZO. So here you can see in the GTO grain size is 8 micron, and here it is, in case of the GZO, it is 2 micron. Okay. So what is the reason for decreasing the grain size? Because you know that this pyrochlore will form a single phase at a very low temperature of about 200 degrees centigrade. But when we put it this one for a very centering at a high temperature for a very long time, you know that it will show the grain growth. Okay, so as a result of that, it is showing a very high grain growth, and this pyrochlore will form a phase at a very high temperature. So it didn't get a time for the grain growth, so that's why the grain size is micron. But one thing is clear, we can say like that when both the sample grain size is order of the micron only, it doesn't matter whether it is 2 or 8 micron from the radiation point of view. So then these material we have put it in particle accelerator, and we have irradiated it. So for that, this one is a facility that we have used it as a IUAC. So there is a particle accelerator is there. So there we can able to irradiate all the ions in periodic table to a very high energy, from kilo electron volt up to MeV energy. So these are the beam line in IUAC particle accelerator. So this one is material science beam line, and then same LINAC beam we feed to the same pelletron beam we will feed to the LINAC beam to increase the energy. And in this one we have some state of art facility, like this one is in situ X-ray diffractometer. So in situ XRD means we have done some modification in standard XRD so that it can be installed in the beam line. So we have designed a vacuum chamber because ion cannot travel in the atmosphere. So the beauty of this setup is that I can irradiate the material, and at the same time I can determine its structure, so that I know how the structure of this material is behaving as I am irradiating. Then another is facility in this one is in situ microgrammar facility. because you know that X-ray diffraction can give only the long range ordering. So if my material will amorphize, so in that case, another important technique is microrama. And another technique that we installed to simulate the reactor-like environment is a high temperature furnace. So this can go up to 1000 degrees centigrade. So I can put my material at 1000 degrees centigrade. That is expected to be core temperature of the advanced nuclear reactor. And at that temperature, I can able to irradiate it, and then I can probe its structure like that. Okay, so for student, this one is how the ion is losing its energy. So I will not go in detail. So if the energy of the ion is kilo electron volt, then elastic origin will be dominated because the energy of the ion is very low. So it will transfer energy to the nucleus, and then some point effect is created. If the energy of the ion is very high, it is order of the MeV. So in that case, you know the energy is very high, then speed of the ion will be very high. So in that case, ion will transfer energy to the electron, and as a result of that, that material will be ionized. And then later on, electron will transfer energy to the nuclei, and as a result of that, some damage zone is created, and that is known as a columnar defects. So you can see this type of defects is created in this type of material, and that damage zone size of this one is order of the few nanometers, and that damage zone is known as a ion track. So this one we have created in this material like that one. Okay, so this one is in situ X-ray diffraction data of pure gadolinium titanium oxide. So this one is crystalline sample or unirradiated sample, and then this value 5 10 to the power 12 ions per square centimeter is ion fluence. Basically, we can say this is the time. So you can say like that we have irradiated material for 10 minutes or like that one. So there you can see if I will add a small amount of the zirconium, so the time required for amorphization is same in the both the case, like 5 and 10 to the power 12 only. Okay, but then I will add more zirconium. So from I increase point from 0.04 to 0.08 and 1.2. So there you can see at this frequency 5 to 10 to the power 12 sign per square centimeter, it retain its crystallinity, and we need to increase ion fluence 2 times to make it amorphize, so that you can see it. Okay, up to zirconium is 1.2. If we will further increase the zirconium, okay, so in these two cases, there we went up to a very high fluence of 1 10 to the power 14 ion per square centimeter. So we have used this high energy 120 MeV gold, and with this much energy we bombarded this material up to time is required for this one is around 5 hours or 6 hours. So with this energy we made irradiating material for 6 hours, and even after that this material doesn't amorphize. Okay, you can see it. So that way it is clearly showing that this titanate is they are readily amorphized, but zirconium is zirconite is they are more radiation resistant. So what would be the reason for that one? So that diffraction peak that we got, we deconvoluted these peaks, this X-ray diffraction peak, and we calculated the area under this curve, and on the basis of that, we calculated the amorphous fraction, and that amorphous fraction you can see it is linearly increasing as we are putting more and more zirconium. But most important thing that we find in this case is as you have seen this data of the crystalline sample. So there we have calculated refinement parameter 48F, and in that one I mentioned this one is that it is linearly increasing, and then there is a sudden jump is there. Okay, and same thing we have observed in this case also, like when the value of the zirconium is 1.6 only. So on the basis of that, we can say that this oxygen is also playing a very important role in this case. And if we can finally control the oxygen in this type of material, so on the basis of that, we can able to design the advanced materials that is more radiation resistance or like that. This data we have published in this Journal of Nuclear Material in 2020. In addition to that, there can be another explanation of this result is on the basis of the bonding. This titanate is they are covalent in the nature, like this one, and this zirconate is they are more ionic. So that's why if we will go with this paper, so same result we can also explain on the basis of that. So that one will be expected to be more radiation resistance. Okay, so that was the case in this case. Another study that we have done is on nanocrystalline materials, because as I mentioned, when we irradiate these materials, so the grain size is fragmented, is converted from the micrograin to nanograin. And in this case, instead of gadolinium, we have taken neodymium. The reason for that one is because this material we are proposing for inert matrix rule, and in that case, we don't mark that this gadolinium is it has a very bad neutrons, so that's why it can able to absorb the neutrons. So that's why we want a material that should have doesn't absorb. So that's why we taken as a neodymium. So, sir, how much time do I have?
5 to 6 minutes.
Yeah, sure, sir. I will complete it. Yeah. Thank you. So, in this case, we have designed, we have used this method for synthesis is this auto gel combustion technique. You know that maximum temperature that we are going in this case is 250 degrees centigrade only. So that's why there will be not any grain growth will be there. And so, this one is crystalline sample, and this one is we treated at a 600 degrees centigrade for 2 hours to get some good microstructure. And then same powder we have sintered at 1013 degrees centigrade for S600 at 1010 at 1300. And why we have done this thing? Because I want to study the effect of the grain size in this case. So how radiation stability will depend on the grain size of the material. So this one is the X-ray diffraction data of these materials. So here again we can see these pyrochlore peak are clearly visible in these two samples, but in S600 we didn't get any pyrochlore structure peak. So on the basis of XRD we can say like that when this is in defectful right phase. But there are another technique, complementary technique that we have used to confirm this phase. So this one is scanning electron microscopy. So their grain size of this sample is varying for this S600 15 nanometer and for S13 into 15 nanometer. So by just changing the temperature, we can able to change the grain size from the 50 to 15 nanometer. And these three samples we have exposed to the IM radiation, and this is the value of the density also. Okay, then we also confirm same thing by using transmission electron microscopy. So there we can see clearly fringes are there, and again that lattice fringes that we have seen from this one for S600, they are same like for the pyrochlore phase. So although XRD didn't show the pyrochlore phase, but by using TEM and this selected electron diffraction pattern, we can able to again confirm it. And then another technique that we use to confirm this pyrochlore phase, particularly in S600, is Raman spectroscopy. So all the mode that is representing the pyrochlore phase, they are available in this one also. So then we have done irradiation of these materials. So these are the data for the irradiation for these three samples. So there you can see S1000 and S1300, they are amorphized at a 5 to 13 cyan per square centimeter. But this S600 sample doesn't amorphize even a very high fluence. So this is clearly showing like this thing, this nanomaterial is showing better radiation resistance in comparison to these higher grain size materials. So to explain this data, we have done fitting of this data by using direct impact model and multi-step damage accumulation model. And these are the results. So these are again amorphous fractions that we have calculated from X-ray diffraction data. So there you can see in case of the direct impact model, the track size, the damage zone we have created, there is no consistency is not there, like 3.4, 4.4, and 3.6. Okay, so in case of the multi-step damage accumulation model, in that one is like first ion will become, and then we will also consider the effect of the first ion when we will consider for the second ion. So there that amorphous fraction that we have calculated is 2.6 for S600 and 4.8 and 4.4 for these two ones. So there it is clearly showing that damage zone created by heavy ion in this nanomaterial is smaller size in comparison to this thing. So on the basis of that, we clearly explain it. And in addition to that, in these material, some anti-side effect formation region is also created in that one. So then again, these are the transmission electron microscopy images of the irradiated sample, and there whatever the track size that we have calculated, so same has been confirmed by using TM also. So finally, I will conclude my talk. So mainly I discuss the radiation stability of these ceramic materials. So in that one, I studied the effect of the composition, and in that one I mentioned like that one titanate pyrochlore can really amorphize, and where zirconate are radiation resistance to the swift wave radiation, and that radiation stability will depend upon Ra by Rb. And in addition to Ra by Rb, we calculated this 48F oxygen parameter. And on the basis of that, we mentioned this oxygen play very important role to determine the radiation stability of these pyrophore. In case of the nanocrystalline material compared with the bulk one, so we found that nanostructural material show better radiation stability than the bulk one, and that we have explained on the basis of this multi-state damage accumulation model. So finally, I will like to acknowledge because this work has been done not by me, because it is by PhD student. So this composition effect has been done by Dr. Ajay Kumar, and Saurabh has done work on this radiation stability of this nanostructural material. And this project is we are doing under guidance of Professor A.K. Tyagi from the Chemistry Division BRC and Dr. Vinita Gupta. And we are also discussing with Professor J. Lian from Rensselaer Polytechnic Institute in USA. And this project is funded by BRNS and from the SCRB. And I also acknowledge IUAC for all the facilities and particle accelerator beam time, and from JNU also. And thank you very much to all of you. And Jai Hind. Thank you.